Hello everyone. In this video, we are going to take the scalable architecture further. Last video, we saw how we can have a highly scalable chatbot, how to split each subsystem of the chatbot into a microservices architecture so that each component can be independently scaled depending on the need or depending on the load. Now, when it comes to database, this is way more complex. Some 6 years ago, I have written an article on how to have a distributed database. If you search, you will find my article in Medium. Hi, welcome to Techie Talks AI. I'm Sri from Shogini. On this channel, we showcase hands-on demos and insights into AI automation and no-code tools. We have created several Make.com modules to simplify no-code automation for you. Subscribe and join us on this journey into the future of technology, where we will use a message broker to ensure that the updates from the master is distributed across all the slaves. These slaves are the ones that are going to stay with the scaling component or the pods, so allow the scalable database. So the master database stays as a single entity where all the updates happen. So when it comes to vector knowledge base, this is an ideal mechanism where we don't need to update the vector knowledge base constantly. So the write operations are minimal. Frequency of writes are minimal. The read operation is what is needing scaling. So this project demonstrates a robust scalable architecture for vector similarity search using PostgreSQL with the PG vector extension. The core of our setup is master-slave replication system, which ensures high availability and distributes the read load, preventing a primary database from becoming a bottleneck. Why this setup matters in agentic AI systems? Imagine you are building an agentic platform, a living network of intelligent agents reasoning, planning, and storing knowledge at scale. Every decision, every memory, every embedding these agents generate must be instantly reliable, highly available, and safe from downtime. That is where the master replica PG vector cluster comes in. At its core, this setup gives your AI system a high availability vector memory, the brain cells of our autonomous agents. The master node acts as the primary cognitive hub, continuously writing new knowledge, that is embeddings, context vectors, RAG indexed, and interaction summaries. The replica node mirrors every update in real time through PostgreSQL streaming replication, ensuring that your agents can keep reading, searching, and reasoning even if the primary goes down. This will continue to happen even if the primary goes down. In a world where multi-agent systems generate millions of embeddings per day, this architecture transforms from a demo to a foundational scalability pattern. You get read scaling by routing heavy vector similarity queries to replicas. You gain fault tolerance. Your agents never lose memory. You ensure consistency across distributed cognition, a crucial requirement for synchronized agent teams. This simple Docker Compose is the seed of an enterprise-grade architecture where each AI agent has a consistent vector memory. Every insight is replicated and query ready in milliseconds. Your intelligent system stays up even when parts fail. So what starts as a neat 2-container demo is actually your blueprint for building resilient, horizontally scalable AI cognition. Because in agentic systems, memory reliability equals intelligence longevity. So again, in a world of agentic AI, memory isn't just data, it is the soul of intelligence. Every decision an AI agent makes, every embedding it generates, every context it recalls depends on how fast and how safely that memory can be stored, shared, and scaled. So that is the reason we have built a master replica PostgreSQL setup with PG Vector, a powerful self-replicating brain for your agentic system. First, let's see this in action. I am in the folder that contains the Docker Compose.yaml. Remember, I will share this code for you to experiment with. Docker Compose down -v. Let's clear all the containers and the volume. And Docker Compose up. Let's run it in the foreground itself. Okay, so it has started the master and the replica. Okay, replica started streaming. I have created a demo.py right into the master node and see if the replica receives it. So this is how I run it. We will see the Python code. See, inserted ID1 into primary, replica has it. ID1 inserted on primary, watch it appears on replica. So let's add one more entry. Okay, ID2 inserted and it is available in the replica instantly. Okay, so that is a short summary, because this master slave replica demonstration, this is all we can demonstrate. So let's go over the components. So Docker compose.yaml is the mechanism that Docker allows us to create multiple containers as a collection of services within the same bridge network. So here we have the primary container, which is the master database. So that is the master database. Then we have replicas. So when we write data into the master will push the data, stream the data onto the replicas. So here we have the primary, which is the master. Then here we have the replica, which is one sample replica, but you can duplicate this section to create your own additional replicas. That is the Docker Compose, and this Docker Compose also has the health check, which will use pg_isReady of the vector database. Okay, so both this master and slave has health check to ensure that its availability is monitored before it is made accessible. Okay, so that is the Docker compose.yaml. And now in replica, we have a bootstrap script. What this will do is this will ensure that every new replica that gets added to this system has the essential schemas loaded. So here it says waiting for primary to be ready, and ensures that data directory is initialized, cloning base backup from primary, and then finally it starts the replica. Then in primary, we have an init script that looks like this. That will ensure that essential vector database schema is loaded into the primary master database. So when master starts, this this 01_init.sql runs to ensure that master is ready to be used as a vector database. So this 01_init.sql is executed when the primary database is first created. This script creates a table named vectors with two columns, ID and embedding. The embedding column is of type vector3, meaning it will store three-dimensional vectors. So here, vector 3. When you go live, this updated with the number of vectors that you need, like 1, 5, 3, 6, etc. Okay, embedding dimension. So here is a demo where we use three-dimensional vectors. It also creates a user replicator with replication privileges, which the replica database will use to connect and replicate data. Now let's look at the replica folder. The replica folder has a bootstrap.sh script. This is the bootstrap.sh script. This script is the entry point for the replica service. It awaits for the primary database to be ready and then uses pg base backup to create an initial copy of the primary data. It then creates a standby.signal file and configures PostgreSQL.conf to make this instance a hot standby, meaning it can serve and read queries. Now let's look at the demo.py which we ran. So here, first section we insert on the primary database. Here we are executing this insert into items, embedding, and a note. Okay. And the note is inserted on primary. Watch it appear on replica. So this three-dimensional embedding and this note, they both get added to the master. And then we will poll the replica to see if the data has arrived. See, embedding and note from items. It fetches one data, and if there is a record, it will print, replica has it, and it will print the retrieved data. Otherwise, it will say it is waiting for replica. Okay, so that is how it runs. So let's try it again. So inserted ID 3 into primary, replica has it 3, inserted on primary, watch it appear on replica. So that is a demo. And there you have it, fully functional master save replication setup for PG Vector, orchestrated with Docker Compose. This architecture provides a solid foundation for building scalable and resilient AI applications. By separating read and write operations, we can ensure that our application remains responsive even under heavy workload. The use of Docker makes it incredibly easy to deploy and manage this stack in orchestration platforms like Kubernetes. Thank you for joining me in this demonstration. I hope this has given you a practical understanding of how to implement a scalable vector search solution. The link to the code is in the description below, so be sure to check it out and try it for yourself. Happy coding. Bye-bye. Thanks for watching. Please like, share and subscribe. Your support really helps. Have ideas or suggestions? Drop them in the comments. Let's build together. At Shogini, we offer expert NoCodeMake.com and Python AI automation consulting with ready-to-use modules to jumpstart your projects. Stay tuned and subscribe for more.